right, we're going to go ahead and begin our notes on standard deviation. One of the most critical and most important um, aspects of all statistics, okay? So it's very, very important that we really understand what this concept or what this thing called standard deviation is. All right. So standard deviation has to do with the spread of the data. Currently, we know two ways to measure spread. We know range, which is your high minus low. So we can see that broad spectrum of the variability. And then interquartile range, so that we know that middle 50%. Okay. But something else that is a measure of spread is this thing called standard deviation. And so we typically represent it with this letter S of X. Now, do keep in mind this, because this will go along with some things that we have to do with later. This lowercase sigma, that would be the standard deviation of the entire population, say like all Aledo High School students. That would mean we would know how long it takes students to get to school for every single student, okay? But S is what we would use and what is mostly used, I think, because samples are more common to get than knowing every piece of the population. All right. So let's go on and let's take a look at this formula. Really want us to understand this formula. Okay, so this formula right here is the standard deviation formula. It looks really scary. And we will do a lot of standard deviation calculation by not by hand. We'll actually get to the point where we just get it with our calculator a lot of the times, okay? But you have to have a fundamental understanding of what the standard deviation is, and you do actually need to kind of understand the makeup of this formula. I also know in colleges, there are quite a few professors who have you compute the standard deviation by hand instead of just relying on technology to do it. College Board focuses more on your interpretation and understanding contextually what standard deviation is instead of the manipulation and the computing of that standard deviation. But we will do some computing here at the beginning. All right, so look at this big old scary formula here. So first of all, we're going to today in class, I'm going to line everybody up, and we're going to line everybody up by their heights from least to greatest, okay? Just because it'll be easy to tell things that way. It's not a requirement. You don't have to line them up from least to greatest. We're going to figure out what the X bar is. X bar is the mean of X's. So if X is all our heights, we're going to figure out what the average, so that's this little piece right here, average of all our heights is. So the standard deviation is representing the typical or average distance all the data is from the mean. So we need to figure out how far away every piece of data is from that mean. And that is then called this thing called a deviation score right here. So we're going to see how far away everybody's height is from the average height. Okay? People that are shorter are going to have negative numbers because each one of these X with a little I is the individual pieces of data. Okay, right here. So everybody's individual height. So we're going to have everybody tell us their individual height minus the mean. So smaller will be a negative result. Bigger than the mean will be a positive result. Okay? So what happens is if I took all of the shorter people than the mean and all of the taller people than the mean, and I had those differences, if I added that together, if I summed them all up, which is what this capital sigma is doing here, if I summed up all of those differences below and above the mean, they would sum to zero. All the ones below, all the ones above would average out to zero. And so that is actually an important fact that you do need to know, that the sum of all of those deviations, the ones below, the ones above, is always zero, which brings us to why we square those deviations, okay? So we square those deviations for this reason. If we didn't square them, the sum would be 0 and not give us any information about the average distance. It would look like the average distance from the mean is 0, when that's actually not the case. So we square them. Now, as a little aside, I always wondered, why do we not just take the absolute value of them? And so the textbook author of our book wrote on a Facebook feed why that is. He said that the function that you would get based on taking the absolute value of things is a polygonal relationship, much more complex than a parabola, which is the quadratic. So what happens is whenever you do differentiating and calculus and that kind of thing, it actually is easier to do the differentiating and the calculating of such values based off a squaring of it and the parabola. So, FYI, and I had always wondered, and he wrote that just recently. That's why we actually do the squaring instead of just taking the absolute value. Okay, so we get all those distances. So you get, everybody then will have a squared number. So all the people on the left of the mean, they're going to square their distance. All those people on the right of the mean, they're going to square their distances, okay? Then we get the average. You know how the average is. You add them all up and divide by the number there is. All right? But, dun, 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 look at what we're doing. We're not dividing by n, which n, by the way, is the number of people in the sample. So if I had 30 people in the class, n is 30, okay? So we're dividing by n minus 1. Why is that? Okay, so here's why. Here's a little explanation of why we're dividing by n minus 1. If we had the entire population's data, we would divide by n, okay? But I'm estimating the height of all of the maybe seniors in Aledo High School. Okay, so or the variability. I'm estimating the variability of all of the students in Aledo High School, and maybe I clustered by my class. So it's a sample. And the reason we're going to divide by n minus 1 has to do with this. When we have just a sample of data, we know that there's got to be somebody who's taller than person in our sample, or even shorter than the person in our sample. So we know that the actual population is actually more varied than our sample, okay? Because if you had somebody shorter than our sample, they're farther away from the mean. So that makes that average distance from the mean bigger. If I had a really, really, really tall person, somebody who's 6'7" in the high school, in the senior class, well, that person's not in my personal class here. I think the tallest student I have is 6'5". Well, anyway, so in the population, there's probably somebody that's even taller away from the mean than my students. So that's more varied. Okay. So we have to account for that. And we have to say, okay, let's be on the safe side. So to be on the safe side, we're going to divide by n minus 1 rather than just n. And let me kind of just give you some quantities to compare that. Think about if the sum of our squared heights was 100. If we divided by n, if we had, say, 9 pieces of data. Hold on a second. Oh, yeah. If we had 10 pieces of data, if the population was 10 pieces of data, they sum to 100, then 100 divided by 10 is 10. But 100 divided by 9 is 11.11, which is a little bigger. So we're keeping it safe, and we're saying, oh, the variability probably is not 10. It probably is a little bigger than that 10, so we have 11.11. Okay, so we're doing it on the safe side, dividing by n minus 1 because it's a sample. All right, we use that larger standard deviation because the population is most likely more variable than our sample. All right, so let's scoot on back here. So we divided by n minus 1, and then we take away that squaring. So then we unsquare root it, and that's what this is here. By the way, if you notice from right up here, before you square root it, what you have is this vocabulary word called the variance. Okay, we don't use variance very much in this class. We use standard deviation much more. But you do need to know the vocabulary that variance is the square of that standard deviation right here. Variance is what you have before you square root it. Okay, variance is the squared of the standard deviation. There are other statistical tests and other classes past this that use variance. Like, for example, the very next hypothesis test after this course is called ANOVA, which is analysis of variance. Okay, so there are other statistical tests that use that variance, but we do talk mostly about the standard deviation. All right, so all of that is kind of giving you an idea of what this thing called standard deviation is. Now, FYI, this I take you through some actual numbers since you're not having the class data. So consider these data sets here. Now look at here, look at their averages. So these numbers 33, 31, 32, 36, 31, 31 average out to be 32.3. Look at these numbers here 22, 34, 58, 52, 10, and 21 have the same average. Okay? But look at the difference in their standard deviation. And the reason, of course, is because data set 1 is much more closely clustered around the mean. Closely clustered, has less variability. So it has much smaller standard deviation than data set 2, which is much more varied. So the average distance from the mean is quite a bit larger. The average distance from the mean is what that standard deviation is. In fact, I have a little song, average distance from the mean, from the mean, from the mean, average distance from the mean, standard deviation. So you've got to really understand that that standard deviation is the average distance from the mean. All right, so I think the rest of this takes you through computing it. This also down here takes you through kind of the formula. It shows how, here we had the mean, and we took how far away those distances were from the mean, and we square them and everything. It basically takes you through what I visually did with you. See, here we have those squared distances. Okay, we sum up those squares, and then we divide by n minus 1. That gives us the variance, and then we square root it to get the standard deviation. It's basically just an example of that formula I already went over with you. So standard deviation, average distance from the mean, from the mean, from the mean, average distance from the mean, standard deviation. Okay. So now here is another example of standard deviation in the real world. So we've got some top 10 rushing leaders, all right, some of football. So here we have these people. And so look here. So they have, this is their variability of their rushing totals each game in the season. Okay, so through the season, there's their rushing variability. All right, so here we go. So the computation, this standard deviation has already been computed for all of those players. So we can see all of these players. So what we do is we talk about two players that had similar averages. So two players that have similar averages we want to discuss, Stephen Davis and Corey Dillon. Stephen Davis had an average of 87.9 per game. Corey Davis, 89.7 per game. So they were very similar in their average production you expect to get per game. Okay? But look at what a key difference is. Stephen Davis's variability is 34.1. Corey Dillon's variability, 73.2. That tells me he's all over the place. Sometimes you get a really, really sucky game from him where he might even have negative. You can have negative. And then sometimes we have positive. Okay, way, way positive, and that'd be awesome. Okay, but sometimes he is really, really hurting us down here on the negative end up to being really, really, really good. So I've asked my football players, what do you think that the team would prefer? Which one of these players would the coach want? And year after year, they tell me Stephen Davis is the way to go because Stephen Davis is preferred because the means are similar, but Stephen Davis is much more consistent than Corey Dillon. Consistency is a good quality to have because the results are reliable, the results are predictable. Okay, so we know it's going to be closely clustered around the mean. We know what to expect, and that analysis of variance test kind of even focuses on that past statistics. So small standard deviations are a desirable trait because of reliability. All right, so now we're going to mathematically do a problem. Let's do it. Here we go. So Consumer Reports in April of 2017 had the following gas mileage reported for these particular 5 brands of Subaru. So there were these different cars, the Tribeca, Forester, Impreza, Legacy, and Outback. And those are the 5 average miles per gallon that they get. All right. So we want to figure out standard deviation. So let's look at this formula again. So the very first thing that we need to do is compute the average. So I added them all up, divided by 5. There's 5 there. Okay. All right. So our average is 19.6. Now, I happen to also ask you the median because we're going to be comparing mean and median here shortly. So look here. The average was 19.6 and the median was right here in the middle, 19. By the way, the IQR was the Q3 22 minus Q1 18, so the IQR is 4. So the middle 50%. Okay. All right. So here's how we do this computing. We take, see, look here, let's focus. Each individual x, subtract away the mean. So let's do that. And then we square it. So here, look what I did. Here is the individual observation. Find its deviation score, individual observation, find its deviation score, its distance from the mean, and then square that deviation. Get the squared distances. So there's the 16 minus the mean and square it. Okay, the next one, 18 minus the mean and square that value. 19 minus the mean and square that value. 22 minus the mean and square that value. And 23 minus the mean and square that difference. Okay, so that is this component here. Now look at this sigma, capital sigma. Sum up those differences. So we're going to come down here. We're going to take all of these differences here and sum them up, and we get 33.2. All right, now we're doing the average, and we're dividing by n minus 1. Okay, remember, because this is a sample. And so that is so we have 5 pieces of data. So n minus 1 is 4. So I'm going to divide by 4, and I get 8.3. And that is what the variance is. So that is your variance. Now, to finish this off, you square root it to get the standard deviation of 2.88. So, in summary, our mean and median were similar, but our variability, fairly close. We got 4 for the IQR and 2.88 for the standard deviation. So the average distance that these pieces of data, average distance that 16, 18, 19, 22, and 23, the average distance those are from the mean is 2.88 miles per gallon. All right. Now, you are asked to do this again. Suppose that Subaru Impreza is now a hybrid car and actually gets 44 miles per gallon instead of 23. We need to recalculate. Oh, poo. Look, I wrote this wrong. 16, 18, 19, 22, not 23, but 44. Okay? So we should have that 44 in there instead of 23. Okay, so there's 44, not 23. Okay, hopefully I did the calculating right. Pooh, I didn't. So we got to fix that. Okay, so what ends up happening is we do need to make sure, dang, I wish I would have had that right. So we're going to have to recalculate. Okay, so did I do even the correct average? I don't know. Let's see. 16 plus 18 plus 19 plus 22 plus 44 equals, divided by 5, 23.8. Yay. Okay, thank goodness. I at least had done the correct mean using the 44. Okay, so, phew, the mean is 23.8, which, do you remember what it was previously? Previously, the mean was 19.6. So, of course, having that higher outlier, notice what it did? It brought the mean way up, okay? Overall average way up. Then I do the individual distance from the mean and then square it. Individual distance from the mean and then square it. Individual distance from the mean and then square it. Individual distance from the mean and then square it. And here's the one that I did wrong. So let's fix it while we're at it. So I should do 44 minus 23.8 is 20.2. So that means that this number right here, okay, so of course, I'm going to just retype that line. So this line should be corrected as 44 minus 23.8, and that equals 20.2, okay? And then when I square that, so 20.2 squared is, I don't think I have the thing, squared is 408.04. Holy cow, right here. So I have, instead of this number here, I have 408.04. 408.04. All right. So now what am I going to do with all of these numbers? I'm going to sum them up. And so I'm going to get a new sum, and I'm going to divide by n minus 1. So my new sum, 408.04, plus all of those other things, 23.04 and 33.64 and 60.84. Okay, 528.8. Hopefully that's right in my haste. So that sum is 528.8. And so that, if I then divide it by 4, I'm going to get 132.2. 132.2. All right. So that is what then my variance should be. Somehow that doesn't seem right. Something seems weird there. The 31 seems right. Anyway, so I'm just going to keep going because 132.2, if we then take the square root of that, then we get, nope, if we do the square root of 132.2, then we get 11.49. Actually, I think that is right. So we get the square root of that, so the standard deviation is 11.49. So, sorry that those calculations were wrong, but we can see that our standard deviation increased a lot. Our standard deviation was 2.88. Holy cow. So because of this outlier of 44, our average distance to the mean is huge now. It's 11.49. Okay, so the measure of center was affected by the outlier. It went from 19.6 to 23.8, even though the median stayed the same. Okay, look, our standard deviation increased from 2.88 to not 5.51, but it was actually, that 11.49. And the IQR stayed the same at 4. So, in summary, another little thing that I want you to know from this activity is that the mean, the average, and the average distance from the mean were definitely affected by that outlier. But the mean and the IQR were not affected by by the outlier. So just a little additional piece of data information that we're going to be getting into. Very, very important that the median and mean and standard deviation were affected. The median and IQR were not affected by that outlier. Okay, so I hope that you now have a good sense of what standard deviation is, and you've got a feel for how to physically calculate that standard deviation. And so what you'll be doing, of course, is the next page in your packet to practice standard deviations and its topics.